After analyzing the longitudinal and transverse susceptibilities of antiferromagnets, now we will look at the case of polycrystalline samples or powder samples. So in these samples, all angles with respect to the field are allowed. So in a powder or polycrystalline sample, all orientations with respect to the field are allowed. Now let's draw our A and B sublattice magnetizations. Let's say this is my A sublattice magnetization, this is my B sublattice magnetization, and the applied field is at an angle theta with respect to the sublattice magnetizations, and I'm trying to find the net magnetization in the direction of the applied field, so in order to get the powder susceptibility. Now, as for the longitudinal component, M longitudinal, I will have the magnetic field component along the direction, along the axis of A and B sublattice magnetizations. I will have longitudinal susceptibility multiplied by H cosine theta. And as for the transverse magnetization, I will have transverse susceptibility multiplied by H sine theta. So this is basically going to give me M parallel, and here I have M perpendicular. And if I want to calculate the net magnetization in the direction of the magnetic field, this will be M parallel cosine theta plus M perpendicular sine theta. So I will find that the net magnetization is longitudinal susceptibility cosine square theta plus transverse susceptibility sine square theta. So the net magnetization divided by the magnetic field, applied field H, will be equal to chi parallel cosine square theta plus chi transverse sine square theta. And now this is for one scenario where I have an angle theta between the A sublattice magnetization and the applied field H. In order to get the susceptibility of a powder, we need to average over all possible angles. So the susceptibility of one crystal orientation must be averaged over all angles theta. So the answer we're looking for, the powder or polycrystalline susceptibility, is chi longitudinal average value of cosine square theta plus chi transverse average value of sine square theta. So we need to calculate the average values of cosine square and sine square theta in order to get the powder susceptibility. Now, how do I calculate the average value of cosine square theta? Average value of cosine square theta is the integral over all possible theta values from 0 to pi cosine square theta multiplied by probability of having that angle theta d theta. Since this is an average of cosine square, the answer should be positive, absolute value. And similarly, the average value of sine square theta will be the absolute value, integral from 0 to pi, sine square theta, p of theta, d theta. Theta can take values from 0 to pi. And the way we have calculated this probability density, or probability of theta, d theta, was considering the spherical surface and the area that is swept by this ring is basically 2 pi r sine theta. So remember, this is our r sine theta here, and 2 pi r sine theta is the circumference. If I multiply it by r d theta, I get the surface area, and when I divide the surface area 2 pi r sine theta r d theta with the total surface area of the sphere 4 pi r square, I get the probability density. So I recall that my probability density p of theta d theta that I have found here is basically 1 over 2 sine theta d theta. So I'm going to use this probability density. Okay, so let's calculate average value of cosine square theta. Its absolute value of the integral from 0 to pi cosine square theta, the probability density sine theta d theta divided by 2, absolute value, and this will be equal to 1 over 2, and if I call u as cosine theta, du is sine theta d theta, it will be actually minus sine theta d theta, and so you can see that you will have in absolute value here u square integral from 0 to pi, and when cosine theta, when theta is 0, u is equal to 1. When theta is pi, u is equal to minus 1. So I should change the limits here as well. The limits will be when theta equals 0, u equals 1, to theta equals pi, u equals minus 1, and u square du. So forget about the minus sign because this is an absolute value. So this will be equal to 1 over 2 u cubed over 3 from 1 to minus 1 absolute value. So we will have 1 over 6 minus 1 absolute value. So this will give me 2 over 6, which is 1 over 3. So the average value of cosine square theta is 1 over 3. Now let me think about the average value of sine square theta. This will be the integral from 0 to pi, absolute value, sine square theta, sine theta d theta divided by 2. So this will be equal to 1 over 2 absolute value integral from 0 to pi 1 minus cosine square theta sine theta d theta, and so I will obtain two integrals, 1 over 2 integral from 0 to pi sine theta d theta minus the integral from 0 to pi cosine square theta sine theta d theta. So this will be equal to 1 over 2. The integral of cosine, sine is minus cosine theta evaluated between 0 and pi, and then minus, I have the same integral I have encountered before, which is which basically gives me, if you remember, 2 over 3. So I can redo it. So it's going to be, when cosine theta is 0, u is 1. So this is an integral from 1 to minus 1 u square du. So we called cosine theta u du, so we had a minus sign here, so this becomes a plus, and absolute value of this quantity. So we have 1 over 2 cosine theta, when theta is pi, is minus 1, so we have 1 minus 1, so we have plus 1 here. So we have 2 from this contribution, and here I have plus u cube over 3 from this integral, u cube over 3 evaluated between 1 and minus 1. So this will give me 1 over 2 plus minus 1 cube, so minus 1 over 3 minus 1 over 3 minus 2 over 3, so 2 minus 2 over 3, so this will become 1 minus 1 over 3, which is 2 over 3. So the average value of sine squared theta is 2 over 3. Therefore, we find that the powder susceptibility, or polycrystalline susceptibility, it was cosine squared chi parallel, so it is chi longitudinal divided by 3 plus 2 over 3 chi transverse. So this is the powder susceptibility. Now if I plot this, so I remember how the susceptibility in the longitudinal and transverse cases varied with temperature. So let's label our nail temperature here. First of all, above nail temperature, I know that the susceptibility drops as C over T plus theta. And below the nail temperature, the longitudinal susceptibility starts from 0 and approaches the value at the nail temperature. So this is chi transverse longitudinal, and the transverse susceptibility is a constant. So this is chi transverse. And if I look at 1 over 3 chi longitudinal plus 2 over 3 chi transverse, basically I will obtain something in between. So the powder susceptibility does basically something in between. It takes 1/3 of longitudinal and 2/3 of the transverse susceptibility. So it approaches the nail temperature like this, and after nail temperature, once again, we're dropping as C over T plus theta. Okay, so to summarize, we have looked at the case where we have a magnetic field applied at an arbitrary angle with respect to the A and B sublattice magnetizations. Then we find its transverse and longitudinal components as chi parallel H cosine theta and chi perpendicular H sine theta. The idea is to find the powder susceptibility, the susceptibility in the direction of the magnetic field is basically chi parallel cosine square theta plus chi perpendicular sine square theta, but to get powder susceptibility we have to average over all possible angles. So we have gone through the math and showed that the average value of cosine square theta is 1 over 3 and sine square theta is 2 over 3. So the powder susceptibility is 1 over 3 chi longitudinal plus 2 over 3 chi transverse. And if we plot this, we find that the susceptibility of an antiferromagnet in the transverse case was constant. It was, if we go back to our calculation for the transverse susceptibility, it was 1 over gamma basically. And the longitudinal susceptibility, on the other hand, we showed to be starting from 0 and approaching the transverse susceptibility at the Néel temperature. So we find that the powder susceptibility is in between, and after the Néel temperature it's obeying the Curie-Weiss law.